Now, for the much-awaited central limit theorem. This is going to let us take that normal distribution we've been studying and help us make powerful inferences about populations. The central limit theorem is useful for understanding that most ratios and means are going to be normally distributed. That's the kind of, I guess, cheat. And it's going to help us draw sweeping conclusions. So what is inference, this word we've been throwing around? Why is it important? Really, it's simply drawing any conclusions we have about data. What does the data mean? What are the implications of the data? That's inference. Using that data from a sample to generalize about a population is a kind of and very important aspect of inference. And so we're going to talk about using statistical analysis techniques to help make those guesses or inferences. So, is statistics a kind of magic? Right? We're going to take these small samples and come to pretty powerful and meaningful conclusions, right, about our data. This extraordinary power largely comes from this wacky thing called the central limit theorem. Right? You can think of the central limit theorem as this power source for many of the statistical activities that involve using a sample to make inferences about a large population. This sounds kind of crazy, right? I know it sounds crazy, but we're going to take a look at what drives and is the central limit theorem and how it's useful and what kinds of things we can infer because of the central limit theorem. What the central limit theorem essentially says is that if we have detailed information about a properly drawn sample, specifically the mean and the standard deviation, we can make strikingly accurate inferences about the population from which that sample was drawn. First question. If we take a properly drawn large sample, what is the best guess of the mean of the population? Right? So if I want to know something about the average of the population and I have a sample, where do you think I'm going to get my best guess, right, about the mean of that population? Trick question, the mean of the sample, right? We don't have any other information to get any other guess about what the right mean could probably be. All right, take a moment, pause, and go ahead and watch a first take on the central limit theorem. Then come back and we'll go ahead and talk about the implications and how we use the central limit theorem. Hopefully welcome back. Here we have an example of the central limit theorem, kind of like the one that you just saw in the stat test video. We have a population of 720 playing cards for the game Dragon. Each Dragon card has a strength value of 1 to 8, and there are an equal number of cards for each strength, which essentially implies that they are uniformly distributed. Of the 90 cards, right, they're divided equally into these 8 strengths. This means, if there's no 0, the population average is going to be 4.5, and the standard deviation is 2.29. Now, what do you think happens if we take a look at, right, the population mean? So if you want to take a look at, you're going to take 4 cards, right? So we're going to take a look at the average strength, right, from any 4 randomly drawn dragon cards. So that's a total of 4,096 combinations, and this is what the population, right, of averages, right, or would look like of each hand. here we have 4 samples. You can see even with these small samples, so here the means are 4.25, 5.25, 4.75, and 6, right? You already see it kind of clustering around that 4.5, even with a very small sample of only 4. As we collect more sample means, you will get closer to the population means. Think of this as if you took, right, instead of the 4,036, you took 4,000 sample hands. Don't you suppose that would get really close to the population mean? Right? So the closer our sample size is to our actual population, right? The closer we are to getting the population, the closer our sample is going to be to estimating the true value of the population. I like to think of this in terms of class. Let's say you want to know the average age of the person in our class. Highly inappropriate to ask, perhaps, right? But let's just say you want to know the average age of the person in our class, of the people in our class. If you took the whole class minus 1 person, you'd probably get pretty close to the average. If you took only 1 person in the class, who knows how close to the average you are? If you take 5 people in the class, you're going to start to get closer to that average, right? So the bigger the sample, the closer to the real average you're going to get. But even with relatively small samples, you're probably going to get close to approximating the true average. The cool thing about means is that it doesn't matter. Remember, the underlying distribution of those cards was uniform. It didn't matter. If you start to take a sampling distribution of the mean strength of samples of size 4, right, then you start to get something that looks like a normal distribution. The averages are going to be normally distributed, even if, right, the underlying strength of the cards themselves are uniformly distributed or follow some other distribution. This is cool because when we're going to compare average, the average of this to the average of that, right, we can use normal distributions. We don't need to know, was it binomially distributed or uniformly distributed? What are the rules of, right, the negative binomial distribution? Don't need to know it. If we're comparing means, we're able to use a normal distribution. So sample means for any population approximate a normal distribution. I think there's a couple exceptions. I think they mentioned them in the stack course video you watched. So distributions of household incomes, definitely not normal. The distribution of the averages of household incomes, normal. The spread of the sampling distribution can be different, however. So while, right, we're going to find in a moment that our averages tend to be less spread out than our overall population, which makes sense. It's going to be related. So the more spread out the ages are, right, the more spread out the averages are going to be of the subsets of those little tiny samples that you get. So the more spread out your population, the more spread out your averages will be as well. And so the size of the standard deviation of the underlying population or sample helps determine how spread out the averages are going to be. But bigger samples are going to lead to what we call a smaller spread in the sampling distribution. The size of the sample, n, is also going to help determine how spread out the means will be. So think of it this way. Think back to our in-class example, right? Is if I take a whole bunch of samples of the whole class minus 1. So this time I leave out 1 random person, the next time I leave out another random person. Those averages are going to be really similar to each other, don't you think? we'll leave somebody out. Okay, there might be an outlier that would throw one average off, but for the most part, those averages of almost the entire class are going to be really similar to each other. If I only have 2 people in my samples, those n, right? So n of 2, right? Those averages are going to be much more spread out, right? I grab a couple people, you're going to get some extreme values. The effect of one extreme value is huge on subsamples of 2, right? If we have a 12-year-old genius in our class, it throws off our average completely, right? So, bigger samples are going to have less spread out averages. So to get accurate, or to be able to say that we're able to say something relevant about the average of the population, right, we need to know about the standard deviation, right, how spread out the underlying data is, and the size of the population. So the spread, when we talk about averages, how spread out our averages, we're going to take that standard deviation and we're going to divide it by n, right, by the square root of n to get what we call the standard error. And this provides us an indication of how far sample means vary or deviate from the population means. So remember, those averages are going to be normally distributed, and they're going to be normally distributed with some spread, and that spread in the case of averages is called a standard error. So this is the standard deviation divided by the square root of n. If S, the sample standard deviation, is large, the standard error will be large. If n, the size of the sample, is large, it's going to shrink that standard error. What's cool about big data is you get these teeny tiny standard errors, right? Because you're working with these giant data sets. So it's very cool to watch your standard error shrink and shrink and shrink and shrink and shrink as you have, millions of observations of something. And that's because as we have these giant data sets, as n gets bigger, that size of our sample approaches the size of our population, right? Because remember, our population averages, the population average is just the average. So we're getting closer and closer to that true average as our sample size gets bigger. So calculate some standard errors for me. See how your math skills do today. Take a pause in the video. If the sample standard deviation is 15, calculate the standard error for a sample size of 25 and 30. All right. For 25, you're going to take that standard deviation of 15 and divide it by the square root of 25, and that's going to give you, right, divide by 5, and that's going to give you 3. If we increase that n to 30, it's going to give us something like 2.74. So we're shrinking that normal distribution and how spread out it is as we increase our n. So here's what we've said so far. As we collect sample means, we get close to the population mean. But each sample mean we have has some chance of error. We don't expect any sample mean to be exactly the same as the population mean. We simply expect that they get close, and that the more means we had, or the more observations we had within a sample, the closer we would be to that population mean. The sampling distribution for means will be well modeled by a normal distribution, right? Statistics magic there. That means are normally distributed. And the spread of the sampling distribution is related to the spread of the population. Bigger samples are going to lead to a smaller spread in the sampling distribution because that sample spread is defined by the standard deviation divided by the square root of n, or the number of observations we have. And so we can add to our handy dandy table that you can calculate, in R to do this, you have to calculate it yourself. So you take the standard deviation, you can divide it by square root of n, or you can install the Plotrix package and use the formula standard error. All right, let's play with this a little bit more before we set you free to go apply the central limit theorem yourself. We take one properly drawn sample, we use what we know to make inferences about the population from which it is drawn. So let's take some practice about how we would make inferences from one properly drawn sample, right? We've given you these examples with many samples, what many samples would look like. But in the real world, we're typically going to have one sample and want to come to some conclusions. So for the dragon example, suppose we have a sample size of 30, right, with a sample average of 4.5 and standard deviation of 2.3. We can calculate the standard error here of 0.42. Let's go ahead and map that to a normal distribution. So instead of that spread outedness of observations of cards, here we're looking at the spread outedness of the averages, right, of a sample size of 30. 95% of the time, the average of that sample size of 30 is going to lie between 3.66 and 5.34. So we can say that we're confident that the true population mean is somewhere between 3.66 and 5.34. We could shrink that confidence interval if we increase, right, n. So suppose we have a sample size of 100. That's going to give us, sorry, there's a typo on the slide there, right, 0.23. So now our 95% confidence interval is even smaller. It's between 4.04 and 4.96. So regardless of the shape of the population distribution, the distribution of sample means is normal if the sample size is large enough. We can use the sample to calculate confidence intervals for the population mean. And this is the reason that most statistical procedures assume normality or take steps to correct for the lack thereof, because this sort of normal distribution is so very useful for us to be able to draw these kinds of conclusions about averages, and as we're going to see later, ratios. The central limit theorem applies best with large samples, generally for sample sizes greater than 30. You'll see in the textbook you're assigned that they talk about this in the context of smaller samples. And when you have smaller samples, you need to use the t-distribution in testing and confidence intervals. However, the t-distribution looks an awful lot like a normal distribution. It just has fatter tails. The smaller the samples, the less normal the t-distribution looks. The t-distribution looks almost exactly like the normal distribution when we have something greater than 30. So let's go ahead and do a little bit more practice. Here we have a new commanding officer arriving at the centralized contracting office 1 year ago. The commanding officer implemented a new contract processing procedure to reduce the amount of time required to completely process large contracts greater than $5 million. A random sample from before this process change suggests that the work took on average 60 days to complete with a standard deviation of 12. The commanding officer wants to know if the improvements reduce the average processing time for large contracts. So the planning staff is going to use 36 randomly selected data points as the test sample. Can the distribution of the sample means be considered normal? Why or why not? So you should have answered yes, because we're greater than 30 and we're talking about means. So we can use a normal distribution. All right, we can now go ahead and use the normal distribution to help draw some conclusions about averages that we might see using these new programs. So let's go ahead and take a look at our normal distribution. We're going to go ahead and map our normal distribution using not the standard deviation, but the standard deviation of averages, or the standard error. So we calculate the standard error here. Is the standard deviation divided by the square root of n, which will give us 2. And that allows us to go ahead and map our x's. You'll notice this is a much narrower spread than we would expect of the underlying data, right? We'd expect the underlying data to be, separated out by 12s, but the averages are going to be more tightly clustered. Now we can use that to make some comparisons of the averages generated by the new program and the underlying, population of data about the old program. So we're going to use, I have up here our normal distribution as a kind of cheat sheet and the area under the curve, but let's go ahead and ask some questions. If the CEO's improvements have no effect on the average processing time, what is the probability that the sample mean would be 58? So the probability, that is all this area under the curve. And we can figure that out as the 13.5, 2.5, and 0.1, which is approximately 16%. 56, well, we no longer have this area under the curve to worry about. So it's only going to be about 2%. 54, about 1%. So that's suggesting that if you got a sample mean of 54, you'd be pretty confident that this is different, right? That this is a different process, that this is an improved process. 58, there's still a 16% chance that this is actually really just basically the same process, or not an improvement. All right, we're going to practice that some more in class. But for today, I think we've done enough to realize that the central limit theorem has allowed us to use some relatively simple analysis and a little data to draw sweeping conclusions about lots of stuff. The central limit theorem is really useful and at the core of a lot of the sort of understanding and interpretation of many complex models and how analysts approach and understand data. So we'll practice using it and employing it to help us make conclusions about a bunch of the comparisons we want to use. It helps us make sense of the mess of data and understand what we can learn from the data we have and the limitations of the things that we've learned. So, thank you for joining me today. I look forward to working on this some more with you and to taking this a step further next week.